Section 2.7, the derivative as a function. So previously we considered a function f of x, and we could take the derivative of it and we would find things like f prime of 5. And then I said, how about instead of f prime of 5, let's just put in a letter for that, and then once we've calculated the derivative, we'll have it in terms of p, and we can plug in any number after that. It seems a little bit more efficient than plugging in the number initially. And what we're going to do now is say, well, p is just a variable, and f prime of p is thinking of the slope at a particular point, at the x value of p. But I could also just plug in x, because x is a variable, and then at x equals 5, I would just be plugging in 5 for x. And this illustrates that the derivative at a particular point gives you the slope at that x value, but you can also think of the derivative as a function giving you the slope of a particular function at any value of x. And so in this section we basically do some calculations and we talk about some of the properties of this function. So we can now rewrite our definition for the derivative with an x instead of a p, and this is exactly the same definition we had in the previous section. I just put in an x instead of a p. So f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. And now let's see how we calculate that given a particular example. So example 2, we're going to calculate f prime of x, and that's the limit as h goes to 0 of f of x plus h minus f of x divided by h, just like I have here. My function f of x is x cubed plus x. So f of x plus h means I'm putting in x plus h here for x and x plus h there. That's x plus h cubed plus x plus h. Then I have to do the minus f of x, and f of x is just x cubed plus x. All I have to do is write that function right there. And then I divide this by h. Now, this is not too bad. The only problem is this x plus h cubed, that's x plus h times x plus h times x plus h, and that's kind of a long calculation. So I'm going to do that over here on the side, and then once I've got that calculation, I'll be able to plug it in. So x times x gives me x squared, x times h plus another x plus h is 2xh, and h times h gives me h squared, and I'm going to multiply that by another x plus h. X squared times x gives me x cubed, x squared times h gives me x squared h, 2xh times x is 2x squared h, 2xh times h is, I'm going to slide this over a little bit to give me some more room, 2xh times h is 2xh squared. H squared times x is just h squared x, and h squared times h is h cubed. So I can combine these two are like terms. So this is x cubed plus 3x squared h, and then that thing and that thing are like terms. They both have an h squared x. So this is 3x h squared plus h cubed. And that big, long, ugly expression is what I'm going to plug in here for x plus h cubed. So this now becomes, instead of that, I have x cubed plus 3x squared h plus 3x h squared plus h cubed plus x plus h. And then I'm going to distribute this subtraction to each of these. Minus x cubed minus x. My x cubes cancel. My x's cancel. And this is all divided by h. And I am happy now because I notice that all the terms that I have left up here in the numerator have h's in them. So I can factor an h out. When I factor an h out of this, I'll be left with 3x squared. When I factor an h out of this one, I'll be left with 3xh. Factor an h out of there, and I get h squared. factor in h out of h, and I'm just left with 1. That's all divided by h. Cancel out those h's. And when I now cancel those h's out, I can now just evaluate the limit and plug in h equals 0. When I plug in h equals 0, that h will turn into a 0 and it'll kill off that term. This h will also go to 0 and it'll kill off that term. So I'll just be left with 3x squared plus 1 is my final answer. That's the function f prime of x.